Hello everyone. The title of the talk is Laser Technology and Applications. I am Dr. Subhendu Mondal from Holdia Institute of Technology. And now we see that in a quantum system that can be atom, molecule, or any plasma system. So they are if you have in an equilibrium, we can have the absorption as well as the emission process, and at an equilibrium condition there will be a constant relationship between these two absorption and emission. And we know the absorption is a stimulated process, and in case of emission we have both channels open. That is, one is spontaneous emission and another is stimulated emission. So what are the relations between these two? And they are called the Einstein's coefficients, and they are known as A and B coefficients. And we will see that they have a very important role for determining the active medium or laser system. So the Einstein's coefficients are quantities describing the probability of absorption of emission of photon by an atom or molecule. The Einstein's A coefficients are related to the rate of spontaneous emission of light, and the Einstein's B coefficients are related to the absorption and stimulated emission of light. So here you see we have a system. We have a system that is downstate E1 and excited state E2. So let's say in the E1 energy state there are n number of atoms, and in the E2 state there are n2 number of atoms. So the probability of upward transition or stimulated absorption, that is R2 R12 is equal to rho nu into B12, because so if I take the B is the stimulated transition coefficient from state 1 to 2, then we take the B12. And here the probability of total downward transition. So as we know that it can be stimulated and spontaneous emission. So here R21 is equal to rho nu into B21, and that part is this part is contributed from the stimulated emission, and A21 is the coefficient for the spontaneous emission process. So the total probability is rho nu into B21 plus A21. Now, if you have the state or the medium is in thermal equilibrium, so and consider N1 there are N1 atoms in E1 energy state and N2 atoms in the E2 energy state. So in thermal equilibrium, N1 R12 is equal to N2 R2. So therefore, we get from this R relations by simplifying the equation. So N1 rho nu into B12 is equal to N2 into rho nu into B21 plus A21, and that is from there we get the photon density. Here photon density is we get the relation A21 divided by B21 and whole divided by N1 by N2 into B12 divided by B21 minus 1. So here we see this is what is crucial in this treatment. Here the stimulated process, whether it is absorption or stimulated emission, here the probability will be depending on the photon density, that is rho nu. And so to simplify this equation, so N1 and N2 we need to know. So according to Boltzmann statistics, we can get that N1 by N2, that is ratio of number of atoms in the E1 state and number of atoms in the E2 state is equal to exponential E2 minus E1 by KT, where K is the Boltzmann constant, and T is the temperature in absolute scale. And that will give you the exponential h nu by kT, where h nu is the energy separation and nu is the corresponding frequency, energy separation between the E2 minus E1. So yeah, putting this value of N2, N1 by N2, we get in this equation that rho nu is equal to A21 divided by B21 and whole divided by B12 by B21 into exponential h nu by kT minus 1. And so such a situation is achieved in a thermal equilibrium condition for a system, quantum system. And we know that, so from Planck's theory of radiation, black body radiation, the photon density in an equilibrium condition is given by rho nu is equal to 8 pi h nu cube by c cube divided by exponential h nu by kT minus 1. So here we see there is similarity between the two photon densities, and comparing these two equations. So before we are going to compare these two equations, so we will know that what is the relation between B12 and B21. So what is B12? B12 is the stimulated emission coefficient from 1 to 2 state, and B21 is the stimulated emission process from 2 to 1 state. So as these probabilities are same, so whatsoever the system, whatsoever the quantum state is, so stimulated transition process for a particular photon density and a particular number, the transition rate is same. So therefore, we can say that B12 is equal to B21. So therefore, we can get that by comparing this above rho nu and the rho nu obtained from the Planck's radiation law. We can get that the A21 by B21 is equal to 8 pi h nu cube by c cube, and it is so as we can see that so we can say that all A values are equal and B values are equal. So in general, we can write all A as A and all B coefficients as B. So therefore, A by B is equal to eventually we get A by B is equal to 8 pi h nu cube by c cube. And so this is the relation which is known as Einstein's AB coefficient, and the relation between Einstein's AB coefficient. And what is the interesting result we get from this calculation and from this expression is that we see that this relation shows that the probability of stimulated emission decreases rapidly with the increase in the frequency of the photon, okay, or rapidly with the energy difference between the two states. So that means the B means the stimulated transition coefficient. So stimulated transition will decrease with the increase of the energy separation between the two states. That means h nu. So that's why. So this is the crucial that if you don't get the stimulated transition process, so we will not get the lasing action. So for higher frequencies, we don't get the much efficient lasing action according to this Einstein's AB coefficient we get. Now we have that. So what are the various types of laser systems? So we can have the 3-level systems and the 4-level systems. So in 3-level systems, so what happens? In this type of 3-level system, a third intermediate energy level is used to achieve population inversion, and which is required for the laser function. So here you see that here first the atoms are excited from level 1 to level 2, and then spontaneously it comes down to level 2. And here, if L2 become the metastable state, so we will get the population inversion, and then by stimulated emission, we can get the lasing action for transition between due to transition between level 2 to level 1. And in case of 4 level system, we will have latest transition finishes in an initially unoccupied level 2, having started in a level 3. The advantage over the of the 4 level system over the 3 level system is that as the level 2 is here as a the level 2 is initially unoccupied because all the atoms are in the ground state, E1 level 1 state. So the L2 is in unoccupied state. So if we excite the atoms from level 1 to level 4, and by spontaneous process they will come down to level 3, and any atoms come down to level 3. So between level 3 and level 2, we will have the population inversion. And so, and if I get a system in which the level 3 is metastable, so we can efficiently use it as a active medium, lasing medium, and thus laser action is possible if the level 3 is sufficiently metastable. So that is the advantage of the 4-level system over the 3-level system. And depending on the type of medium, we have the various types of laser: solid state laser, we have gaseous laser, we have semiconductor laser, and dye laser. So according to the course, we have to concentrate only on the ruby laser, and for gas laser is helium neon laser. So obviously, first we will describe about the solid state laser, and that is ruby laser. So a ruby laser is a solid state laser that emits red light, and was the first laser was discovered. So you see, a ruby laser uses a synthetic ruby crystal, which is made up of aluminum oxide, and that is called sapphire, with chromium ions doped. Okay, so so this rod is used as an active medium, as it's shown, and and over this ruby crystal rod, we have a xenon flash lamp is wrapped over it. Okay, and it will behave like a pumping system. And this is the structure of the ruby laser, and the light is produced here is 694.3 nanometer red light is produced from the ruby laser. So as you see that the flash lamp, because of flash lamp, because it is not used as we use the flash lamp for exciting the atoms, or for the population inversion purpose. So, and the population inversion are not being take place continuously. So it takes place at a pulsed manner. So that's why the laser light output we get as a pulsed output. So that's why the ruby laser is a pulse laser. And what is the energy level diagram? So it is basically that 3-level system where using a optical pump, we excite to the higher excited state, and from their non-radiant transition, it comes to the E2 state. And then, so these two states are considered two distinct states, and transition from this two excited state, we get the two wavelengths, that is 694.3 nanometer and 692.7 nanometer wavelengths of laser light, which falls in the deep red region. And next, coming to the helium neon laser. So it is the gaseous laser, and here the helium. They are helium and neon gas are taken in 10:1 ratio, and they are kept in a high vacuum tube. And here you see for a population inversion, the electrical discharge is used, so electrical energy is provided. And as the discharge is continuous, so electrical energy is supplied continuously. So that's why the laser light we get continuously. So that's why it is called continuous laser. And energy level diagram for this laser is, so helium and neon, the mixture is taken in 10:1 ratio. So here the physics behind to take helium and neon, because we first the excitation is taking place in the helium atoms, and because the excitation constant probability is larger than the neon, and as you can see that the E3 and E4 states are closely linked to the same neon E5 and E3 state. So therefore, so atoms excited to helium excited state, they will transfer to the neon excited state E5 and E3, and from there it comes down to with a radiation less transition to E2 state, and then so basically this neon E5 and E3 states are the beta stable states. So we get the different frequencies for transition from E2 to E5 to E2 state. We get the 632.8 nanometer of wavelength laser light, and after this coming down to E2, it comes down to E1 state by spontaneous emission process. So these are the types of laser we have discussed. So we can have the various kind of semiconductor lasers and the dye lasers. But in the theory course, we have the only two lasers to concentrate on. And here we come to the applications of laser, because as you have seen that a laser is highly monochromatic light, and it is of highly coherent. So because of this, we get the laser light, the highly directional, and we can amplify according to the active medium system and the mechanism of excitation. So because of these ideal properties, we can use laser in enormous ways. For example, from medicine. So in medicine, lasers are used in medical and cosmetic procedures, such as removing hair, scars, and tattoos, and reducing fat. Even, and they also can be used to coagulate body fluids and vaporize tissues. Okay, so and in manufacturing industry, lasers are used for cutting, welding, drilling, and other material advanced manufacturing, and they are used to cut materials with intricate shape and patterns and join materials with high precision. In communication industry, lasers plays a very crucial role. Lasers are used in optical fiber. So they are used for optical fiber communication network, radar satellites, and in space communication, as well as optical dishes. In optical dishes, we use semiconductor lasers. So lasers are used to read and write data on optical discs, such as CDs, DVDs, scanners, laser printers, and pointers, etc. Also, so laser can be used for power beaming. So laser can transfer power lessly over long distance. So, for example, one can use laser light to charging up a flying drone. so without having the cable connected to it. Okay, as well as the we can use laser to measure precisely the distance between the two distant point objects. So here laser can be used to measure the distance, such as distance uh, from Earth to Moon. And in art and entertainment industry, laser are used in light shows, special effects in movies, and other aspects of arts and entertainment can be included. And these are the application purpose. Not only this, laser is used day by day for advanced research process, and laser are also used in barcode scanners, laser printers, laser pointers, and more, many more. So with this, we finish today's talk, and thank you all for your kind attention. Thank you.